Hello everyone and welcome to OneClass. My name is Jeff Krause. I have a PhD in physical chemistry and today I'm going to run through a few undergraduate level physics questions. So here's our first one. A small spherical mass, m equals 0.35 kilograms, is attached to one end of a light string. So I'm just going to draw this out myself. So the mass is 0.350 kilograms. And the other end is attached to a frictionless pivot that is itself attached to a ceiling. So that's the attachment point. It's released from rest at 40 degrees. And then at the instant that it passes through a 20-degree angle, so that's 20. Maybe I'll do that. Just to make it a bit more obvious. At that instant, the speed is 2.439 meters per second. Okay, and so now for A, it wants to calculate the magnitude of the radial acceleration at the instant it passes through the 20-degree angle. Okay, so the radial acceleration is just A, right? And now remember that F equals ma, which in a centripetal motion is mv squared over r, where v is our radial velocity. So then A is v squared over r. Which is right. So A here is our radial acceleration, which is this value. So that's good. That's what we're supposed to be getting, and it's related to our tangential velocity, which is what's given in the question here. So A is v squared over r, which is 2.439 meters per second squared, over our r, which is given in the question as 1.75 meters. Now if we do this out on our calculator, we get 3.399 meters per second. Okay, so there's our radial acceleration. And now B is to calculate the tension in the string at the same instant. So if we do up our free body diagram, we've got our 20-degree angle. And so we've got mg, and then tension, and those are the forces that are acting. We can separate our mg into a radial and a tangential component. So our mg is straight down. Always mean to expand it. Okay, sorry. mg is straight down. So the radial component here and the tangential component here. And so we can see this is a similar triangle. So that angle there is 20 degrees. And so then this is mg cosine of 20 degrees. And this is mg sine of 20 degrees. Okay, and so then if we look in our radial direction, we have our forces are the tangential force. I'll just get rid of that little vector symbol because I'm just looking in the radial direction. Our tension, which acts straight up, minus mg cosine of 20 degrees. And that equals our ma. So that means that we can rearrange this for our tension. So our tension is just ma plus mg cosine of 20 degrees. And recalling too that our acceleration we calculated is radial acceleration, so it will be in the direction of the tension, so it should be positive. Just to double check some of our directions there. So then our tension is going to be 3.3, nope. Yeah. 0.350 kilograms times our 3.399 meters per second. That would be squared. Plus 0.350 kilograms, 9.8 meters per second squared, and times the cosine of 20 degrees. Now I seem to have missed this acceleration component here, my mistake. So I'm just going to add it in here now. So then our tension is 1.18965 newtons. Oops. Newtons plus 3.8 times 20 degrees cosine, 3.223146, which is equal to 4.413 newtons. So there's our tension. There's our tension there. Okay. And so then checking through the solution here, there is actually no solution given. So then this is all there is. Okay, so there's our question there then, and I'm just gonna say incomplete then. All right. Okay, so for this one, we have a particle with a charge of, and for this, for some of the characters that don't seem to be coming in properly, I'm just going to use charges, at least my best guess for some of them. So we have a charge of 1.9 times 10 to the minus 6 coulombs. And we're moving it from point A, from point A to point B along a distance of 0.28 meters. And it experiences a constant electric force, and its motion is along the line of action of the force. So we've got an E field that points in the direction from A to B. And then we're given that the UA minus UB is 13 times 10 to the minus 4 joules. And then we're asked to find the magnitude of the electric force. So it gives us it like this, which is kind of funny because delta U is always final minus initial, so it should be UB minus UA, which is minus 13 times 10 to the minus 4 joules, which is good because it means that our potential is going down, which it always does. So we always go from high to low. So the fact that it's negative means that we're doing that. So we're asked to find the magnitude of the electric force. I always remember this little square here. So in going from the potential to the force, we take derivatives with respect to distance. And in this case, we can just leave it in one dimension because we're just moving in one dimension. And we're also asked to find the magnitude of the electric field. And so moving from electric field to force, we multiply by charge. And then the other side of this square is the potential, which I'm just going to fill in for completion, like that. So this is kind of the square I use to remember all this. So if minus du by dx is the force, then so that actually makes it easy on us. So our as long as our force is constant, which it says it is, then our force is just minus delta U over delta X. So just taking the differentials and moving them to a delta. So in this case, it would just be 13 times 10 to the minus 4 joules over 0.28 meters, which comes out to be 4.64 times 10 to the minus 3. And now a joule is a kilogram, or is a Newton meter, I should say. So a Newton meter divided by a meter is just a Newton. And so that also kind of validates that we're doing something right here, just because the units work out. It doesn't mean it is right, but it's a pretty good indicator. And so then for B, so looking at our little square here, F is just QE. So then E is F over Q, which is just 4.64 times 10 to the minus 3 newtons over our charge, which is 1.9 times 10 to the minus 6 coulombs, which comes out to be 2,443.6 newtons per coulomb. Okay, and so there's our force and our E field. Okay, now if we check through the solution here, so our charge starting out negative, which isn't so great. dW is F dot dr, so we're getting the same force, which is good, but their delta U is also opposite. But they're also computing work. So direction of the force, not quite, but it's okay. And then the force is coming out to be massive. Why is that? 10 to the 4. It should be 10 to the minus 4, I see. Okay. So there's just a few sign errors throughout here. The E field should be from B to A, taking things in the proper direction. So all the numbers are coming out similar, but I'm just going to say several sign errors and exponent errors. And I'm just going to say it's incorrect. All right. So for this one, we've got a red button is accidentally pushed and it launches an ICBM. The ICBM leaves the sea surface with a speed of 51, I shouldn't have done that, 5,100 meters per second at an angle of 70 degrees. The supervising officer is on a cruiser, 500 kilometers. Behind the sub. She launches a rocket to intercept and destroy the ICBM when it reaches a height of 1,000 meters. 1,000 kilometers, sorry. So this ICBM is going to be in parabolic motion. Similar to that. And then at 1,000 meters, so when this value is 1,000 kilometers, sorry, then we want our rocket to slam into it. And we need to find the constant acceleration of the rocket such that it will intercept, neglect air friction, and the other thing that's given is that the rocket starts 20 seconds after the ICBM is launched. So we just need to find the time where our ICBM reaches 1,000 kilometers, and then use that time to figure out how much time the rocket has to see the force that we need. So first of all, let's expand our ICBM's equations of motion here. So to start off, we've got 5,100 meters per second at an angle of 70 degrees. I realize that angle is nowhere near 70 degrees. I'm just going to make it slightly better than this. So 70 degrees I think would be more like that. So 5,100 meters per second. There's a slightly more accurate triangle. Okay, and so then this guy here is going to be 5,100 times the cosine of 70 degrees. And this one here is going to be 5,100 meters per second times the sine of 70 degrees. And I'm going to call this my Vy, and I'm going to call this my Vx. Just to save me the sake of writing these out all the time. So the x direction will matter, but for now we're just going to concentrate on the y. So in the y direction, we have Fy equals, so if we look at our ICBM as it flies, we've got an mg force, and that's it. We really just, as it's unpowered after it leaves, then that's all we've got. So it's just minus mg, which equals ma. And so then our acceleration is just minus g. And now we can use our kinematic equations and say that our final y is going to be our initial y plus our initial velocity in the y direction times time plus 1/2 at squared. And we have our initial velocity here, so maybe I'll put a little I on these guys just to, maybe 2, just for the sake of not messing up or not having it be too confusing. I'll use this notation instead, like that. All right, so there's my Vyi. My acceleration, my initial y is 0, so I can get rid of that. And in fact, I know what my yf is as well. It's 1,000 kilometers, so I can fill that in. So I've got 1,000 kilometers is equal to my 5,100 meters per second times the sine of 70 degrees times t plus, or not plus because it's a minus g, minus 1/2 of 9.8 meters per second squared t squared. Or I can rearrange this into 0 equals minus 1,000 kilometers. Actually, I might as well put this all into meters. So minus 1,000, and I actually might as well put it minus 1.0 times 10 to the minus 6 meters. Doing that out, that's 4.79243 times 10 to the 3 meters per second t minus 4.9 meters per second squared t squared. So now everything's in meters and seconds, so that's good. I can use the quadratic equation here and say that t is minus 4.79243 times 10 to the 3 meters per second, plus or minus square root 79243 minus 4 times 1 times 10 to the 6. That should be a plus 6, my apologies. Meters times minus 4.9 square root of all over 2 times minus 4.9 meters per second squared. Okay. So then doing out some of this here, so this is 489.023 seconds, plus or minus 1835.044, and that would be in meters per second over 2 times 4.9 meters per second squared. So then our t is 301.774 seconds, or 676.273 seconds. And these two times would just correspond to 2 points on the parabola where it equals 1,000 kilometers. So this point and this point in my rough drawing here. But we're only interested in the earlier time, so we want to hit it at the earlier time. So we're just going to use this time. Okay, so there's our time. To get the distance now that our rocket has to travel, as our rocket needs to travel a distance of 500 kilometers plus plus our x for ICBM, and then in the y is the 1,000 kilometers. Okay, so there's our ICBM motion there. We need to still solve for our x for our ICBM. So we can use kinematic equations again. So xf is xi plus vxit. And recalling from our triangle above, our vxi is just 5,100 times the cosine of 70. And our xi is just going to be 0. So it's just 5,100 meters per second times the cosine of 70 degrees times our time. And so this comes out to be, where was I here? 1744.30 meters per second times our time, which is 301.774 seconds, which comes out to 526,385.212 meters. So it turns out I've drawn this a little bit extended because it's about 500 kilometers. So it's pretty much the same distance either way. So now, now we have our full rocket flight. Now the thing to remember is that we're told the rocket starts 20 seconds after the launch of the ICBM. So that means that the time our rocket has is the rocket time, 301.774 seconds, minus 20 seconds. So the flight needs to take 20 seconds less time because it starts 20 seconds later. And so that makes it 281. So that's our time for a rocket. The rocket is going to travel in a straight line. And we just need to find the constant acceleration of the rocket. It doesn't matter what force is being applied, we just need to know what acceleration the rocket needs. And so for that, we can use our kinematic equations. And so we're just going to use an RF version. So RF is Ri plus V naught T plus 1/2 a T squared. And we're assuming the rocket starts from rest, so that's 0. We're starting at 0, so that's 0. So luckily we just need to know our distance, and we can solve for our acceleration using our time. Now our distance is, this is our r here. And so from Pythagorean theorem, just filling in a couple of things here. So we've got 500 kilometers. We've got our ICBM distance, which is this 526.385 kilometers. And then this is 1,000 kilometers. So then our r is here. So our r squared is 500 kilometers plus 526.385 kilometers plus 1,000, and that should be squared, plus 1,000 kilometers squared. So our r is 1432.992 kilometers, which, put it into meters, is 1.432992 times 10 to the 6 meters. Okay, and so we have from our kinematic equation 1.432 992 times 10 to the 6 meters is 1/2 a T squared. We know our time and we're solving for our acceleration, so it's 2 times this value. Over our time, which we solved as 281.774 seconds, and that should be squared. And this comes out to be 36.097 meters per second squared. And so then there's our acceleration of a rocket that we need to collide with the ICBM in time. Okay, so checking through the solution. So we need to find our time. It comes out to be 301.8 seconds, so that looks good. So we need to find the horizontal range, which comes out to be 526. So that looks good. Just some rounding differences there. For the rocket, it needs to be 20 seconds less, so 281.8. The total distance traveled is going to be the sum. Our initial velocity is 0. So then our acceleration comes out to be 36.1 meters per second squared. So that looks good. Okay. All right. So for this one, we've got 2 blocks on a table, or one's on a table, I should say. Some coefficient of friction. This one is given as 5.1 kilograms, and it's on a pulley, and it's yanking down this 3.7 kilogram mass. Okay. And assuming the system starts from rest, when the masses have moved a distance of 0.381 meters, their speed is 1.32. And it wants to know the coefficient of friction and the magnitude of the tension in the cord. So we've got a couple free body diagrams we can draw here. So for the 5.1 kilogram mass, our tension goes this way, our friction goes this way, and I'm kind of at an angle there, so I'm just going to fix that. So for a 5.1 kilogram mass, our tension goes this way, our friction goes this way, we've got an mg and a surface normal. So in the y direction, really nothing's going on, but so it's not accelerating in the y direction, so that's 0. Our forces, though, are the normal minus mg, which means that which equals 0 from above. So then our normal is equal to mg. So that's all that gives us. Recalling that our friction force is our coefficient of friction times our normal, then that kind of solves for that for us. So in the x direction, our force is our tension minus our friction, which is tension minus mu n, which is equal to ma. Now, one thing we'll have to be careful of is to keep the directions of our masses, that our masses are traveling in the same direction. So that means for a 3.7 kilogram mass, we'll want our motion in this direction to be positive. So for a 3.7 kilogram mass, we would have mg and tension, but we want this to be our direction of positive travel. So in the y direction, our forces are mg minus tension. Although you might want to make tension positive because it's pointing up, we want to make sure everything's still in the same direction of travel. That way we don't have to worry about weird sign things. As this equals ma now. We don't need to worry about the x direction because there's no forces. And also because the systems are connected, these accelerations are going to be the same. And also the tensions themselves are going to be the same. We don't know the tension, but we do know a speed at a certain point. So let's use this equation of motion to solve for the tension, and then we can get our acceleration out. So from this, our tension is mg minus a. And I better be careful here. I should have been more careful throughout here, but I'm going to put 2's on these masses so I don't make a mistake. And I'm going to put 1's on these masses. As the question seems to give us that M2 is the mass on the table. Okay, so there's our tension there. And it should be with correct directionality. Or no, sorry, it won't be with correct directionality. So this tension will be, will come out to be a positive value, but we need to remember that it's in the negative direction, as we've already taken account of our directionality by giving it a negative sign. Okay, so with that value for our tension, we can plug that into our x equation for M2. So from M2 x, we have that tension minus mu n is M2a. And so then we have M1 g minus a minus mu n is equal to M2a. And now we can start to solve for our acceleration. As we have some of these quantities. Oh, sorry. That's just our equation that we can use to get for our mu, but we actually have more information because what we're told is that when the masses have moved a distance of 0.381, their speed is 1.32. So that means, how do I draw this here? So we've got 5.1 kilograms. $3.7. And so once we've moved a distance of 0.381 meters, our speed is given as 1.32 meters per second. And so we can apply some of our kinematic equations here. And now our acceleration is going to be constant. And so, and assuming we start from rest, then our xf is xi plus v naught t plus 1/2 a t squared. So if we start from rest, then that's 0. Start from 0, then that's 0. Then we can now solve for our acceleration. So our acceleration is going to be 2xf over t squared. But also, if we can use our velocity equation, so Vf is Vi plus At. Again, starting from rest, to say that our acceleration, or sorry, our time is Vf over A. And so we can plug this equation into this one to say that our acceleration is 2 times xf over vf over a squared, which is 2xf a squared over vf oh, I see. There's no point in doing it that way, I suppose. Okay, yeah, that's fine. 2xf a squared over vf. So then we can rearrange this equation now. So a is 2xf a squared over vf, just rewriting it. We can multiply out these guys and divide by a to get vf over 2xf is equal to a. Vf squared. Okay, and so now we have our velocity, vf in this case being at the point that it's given us here, so our acceleration is 1.32 meters per second squared over 2 times the distance traveled, so 0.381 meters. And so this comes to be 2.287 meters per second squared. Okay, so there's our acceleration at that point. So if we add that acceleration at that point, so we have our acceleration for our entire motion actually, sorry, because it's constant. So that's the acceleration that we expect. So now returning to our x kinematic equation, then we have m1 g minus a minus mu n equals m2a. So minus mu n equals m2a. And recall that our normal force is m2g. So then we've got m1 g minus a minus mu m2g equals m2a. So now dividing through by m2 and separating this out, we've got m1 over m2g minus m1 over m2g a minus mu g is equal to a. Bringing this to the other side, we've got m1g over m2 minus mu g is equal to a onto 1 plus m1 over m2. And we can actually divide through by g here and solve for mu. So then minus mu is equal to a over g, 1 plus m1 over m2, minus m1 over m2, or mu is equal to m1 over m2 minus a over g, 1 plus m1 over m2. And there we go. Finally, we have an expression for mu. So our mu is M1 being 3.7 kilogram mass, minus our acceleration, which is 2.287, over g, which is 9.8 meters per second squared. Okay, and so working these values out, we get 72549 minus 367 times 0.72549. And so this all comes out to 0.32282. So then there is our coefficient of friction. Now, given our coefficient of friction, we can solve for our tension from either equation. So we could have actually solved for our tension from our M1 equation. So we had that the tension was M1G minus M1A, which is our 3.7 kilograms times 9.8 meters per second squared minus 2.287 meters per second squared, which comes out to be 27.798 newtons. So there's our tension from our M1 equation. We can also solve for it from our M2 equation, and it should be consistent. If it's not, then we've made a mistake. So from our M2 equation, we would have that our tension is M2 times our acceleration, 2.287 meters per second squared, plus our coefficient of friction times M2G, so 5.1 kilograms times 2.87 meters per second squared, plus 0.32282 times our mass times our acceleration due to gravity. And if we work this through, then we get 27.798 newtons. So that looks good. So they're consistent, meaning we did everything correctly. Or at least it seems to be. Okay, so let's check through the solution here. Okay, so we get 0.326, so I believe that's the coefficient of friction. And acceleration of the system is A, which comes out to be 2.288, so that looks good. But then the tension comes out to be 31, which is strange. So the tension should be 5.7, so they used the wrong mass. Wrong mass to solve for tension at the end. Incorrect t-value. Alright. So they just used the wrong mass at the end, but that's a small mistake. This should probably be rectified. Okay. So here's my next one. A point source of light is submerged 2.70 meters below a lake and emits rays in all directions. On the surface of the lake, the area illuminated is a circle. What is the maximum radius that this circle could have? Okay, so this is just a refraction question. So we're solving for our radius given the distance down the light source is. And so we basically need to just solve for what this angle is. Now, this will have a similar triangle, so that's our theta I, and the light is going to refract with some theta F, and we can use Snell's law, so N1 sine theta 1 is equal to N2 sine theta 2. And we can see that these are similar triangles, so this is actually our angle we're solving for. N1 is for water, so that's just 4/3. And N2 is for air, which I'm going to take as 1. So what we have for our equation then is sine theta 1 is equal to sine theta 2. Now, we have some critical angle where theta F or theta 2, maybe I should have actually used the same notations, and I apologize for that. So I'm just going to switch these over to I's and F's, like that. Now when theta F is 90 degrees, we've got our critical angle. So theta I is our critical angle when theta F is equal to 90 degrees. So then we have 4/3 sine of our critical angle is equal to the sine of 90 degrees, which is just 1. So then the sine of our theta critical is just 3/4, or our critical angle is 48.5904 degrees. And so that's our maximum angle. And so then redrawing our triangle here, we've got 2.7 meters. Here's our R, and that's our 48.5904 degrees. And so we can see that R over 2.7 meters is equal to the tangent of this angle, or our R is 2.7 meters times this, which comes out to be 3.06 meters. So the maximum radius our circle can have is 3.06 meters. So our angle is 48.59, and so our maximum angle is this 3.06. And so that looks correct to me. All right. So for this one here, we've got an ion of mass 6.5 times 10 to the minus 15 kilograms. And the charge is some unknown magnitude. It moves in a straight line through a region of space in which we have a uniform magnetic field which points out of the paper. This is my attempts at uniformity. And it also has an electric field which points towards the top. And I have a feeling this isn't very straight. So I'm just kind of going to redraw this a bit here. So let's try to straighten this up a bit. I apparently have some disorder that leads to things not being very straight here. All right, there's our B field. All right. So we've got an E field which points upwards. So that's going to deflect a charge either upward or downward depending on the sign. And we've got a B field that, that comes out of the page, which again is going to deflect the charge in one direction or the other. So this doesn't tell us our, this would tell us our magnitude, but not necessarily our sign. And then it travels into region 2, in which only the magnetic field is present. So there's no E field this time. And the particle is deflected into a circular orbit. And this direction. So already we can get our charge from our B field there. Okay, so our A is indicate the forces which act on the ion at point P1 in region 1. Okay, so assuming a positive charge, then our free body diagram in area 1 is going to be an electric force going this way. And then as it's traveling in a straight line, we'll have to have a magnetic force going in the opposite direction and actually equal in magnitude. Okay, and we can write these as well. So this is going to be QE, and our magnetic force is going to be QV cross B. And if we use our right-hand rule, so we point, so our velocity is this way. So if we point our fingers in the direction of the velocity and our palm in the direction of the B field with on our right hand, and then our thumb will point in the direction of the force. So we can see that the force will point downwards. So this will be minus QVB in the y-hat direction, and we're given our E field is in the positive, so this will be QE in the y-hat direction. So that all checks out. And we can already see now what the charge on the particle must be, as when it enters into circular motion, our force must be this way, right? So for B, what is the ion speed at point P1? P1, so this would be P1 here. We are given various factors here actually. So, all right, so we have F net is equal to QE minus QVB, which equals 0, so that's in the y direction. And in the x direction it would also be 0, but that's okay. And the y direction is all we're concerned with, so QE is equal to QVB. We can see that the charges will cancel, and so our velocity is just E over B, and we're given that this is 2500 newtons per coulomb over 5.0 Tesla, which comes out to be 500 meters per second. So there's our speed. C indicate on the diagram at point P2 in region 2 the direction of the force. So I kind of already did this, but if we're entering into circular motion, then we know that the force has to be towards the center of the motion. And then so D is Q positive or negative. So our force from our magnetic field is minus QVB y hat. But from our free body diagram, we can see that our force has to be in the positive y direction, so Q must be negative. Right, and that way our force will be, so it's like Q is minus Q, where Q is the absolute value of the charge. So then F would be QVB in the y hat direction. That way we can get our centripetal motion. Okay, so now checking through our solution here. So we get an electric force and a magnetic force, which are directly opposing each other. We can use this to solve for a velocity as 500 meters per second. Our direction of our force at P2 must be centripetal, so it must point towards the center of the circular motion. And for this to be the case, it has to be a negative charge. And so that looks good. All right. So now we have a 122-pound person dropping from a height of 20 feet onto a 3 feet tall trampoline and it wants to know what distance this moves. Okay, it gives us the spring constant for the trampoline, and so I'm going to call this delta x, which is equal to 3 feet minus my height. Sorry. Okay, so first of all, we need to do some unit stuff here. So we're given our K as 40 pounds per inch. So a force pound is 4.4482 newtons. A foot is 12 inches, and a foot is 0.3048 meters. So our K here is 40 pounds per inch times 4.44822 newtons per pound times 12 inches per 0.3048 meters, which is 7,005.07 newtons per meter. Our weight is just mg, which is 122 pounds, which we need to multiply by our Newton per pound. conversion to get 542.683 newtons. Okay, so now our initial, we can use conservation of energy here. So our initial energy is our gravitational energy, which is 542.683 newtons, times our initial height, which is 20 feet, times 0.3048 meters per foot, which is 3308.19 joules. And now from conservation of energy, we have that our final energy, or I should say, before going there, our initial energy is just our potential energy. Our final energy is going to be our final potential energy plus, our final potential energy. Now we're assuming when we reach the bottom of the trampoline that there's zero kinetic energy. So it's just going to be potential in both cases. So our final potential energy is going to be our gravitational potential energy. So our final height, mg times our final height, plus our spring potential energy, which is 1/2 k delta x squared. So now for delta x, so if we kind of expand this a bit, so this is 3 feet. This is our height final. So this here is delta x. And so we can see that delta x is 3 feet minus our final height. So then our final potential energy is mg, and our little man is there, mghf plus 1/2 k 3 feet minus our hf. Squared, sorry. And just to do some conversions there, so 3 feet times our 0.3048 meters per foot comes out to be 0.9144 meters. Okay, so from our conservation of energy, we have that UI is 3308.19 joules, and our UF is our mg, which is 542.683 newtons, times our final height, plus our 1/2 of our k, which we solved for 7005.07 newtons per meter, times our 0.9144 meters, minus our hf squared. So now we can expand this in terms of our hf. Times hf. So we're going to have to square that. So this is 3502.535 newtons per meter. And then this all gets multiplied by 0.9144 meters squared minus 2 times 0.9144 times HF plus HF squared. And so working this all through, we've got, and rearranging things to look more like a quadratic equation, 3201.8036, and this will be in Newton meters, minus 5862.753 times HF plus 3502.535 newtons per meter times HF squared. Okay, so now our UI has to equal our UF, and so we can rearrange this, and I'm going to put it into more of a quadratic equation, so I'm just going to skip a couple steps here and say that we're going to end up with a quadratic equation like this guy. So that's just putting in our UI, rearranging in terms of the HF, and then dividing by the A term. Okay. So now we've got a quadratic equation. So we can solve for our HF. As minus B plus or minus root B squared minus 4AC all over 2A. Which is equal to 1.67386 over 2 plus or minus 1.70977 over 2, which is minus 0.01795 or 1.691815. And so these two solutions correspond to the bottom and top solution. So the top solution doesn't make any sense because there's no way it's going to balance up. So only the bottom solution makes any sense. So it would be this value, which is negative. And so it asks, will it bottom out? And it will. So we've gone past the ground here. And so it's going to bottom out by this amount, or putting this into feet, negative 0.059 feet. So HF, so for B, since HF is below the ground by 0.06 feet, roughly, then we need to add a 0.06 foot support. So the support needs to be I would say greater than 0.06 feet. Okay, so get our initial potential energy, set it equal to our final potential energy, So the only issue here is they're solving for x directly, which is doable, but without taking into account your initial potential, your final potential energy. So 3.38 feet. Okay. Okay. So actually you don't bottom out quite that badly. So this final energy here doesn't include the gravitational potential energy, the final gravitational potential energy of the person. So it's putting all the energy into the trampoline, but the person still has gravitational potential energy, and so that actually reduces the amount that it's bottoming out. So I'm going to say that the final potential energy is missing the gravitation, and I'm going to say that this is incorrect. Okay. Okay. So we've got a hollow sphere. Of radius 0.15 meters, and it's on a 30-degree incline. The moment of inertia of the ball is 0.40. So it's given here as 0.40 kilogram meters squared. But if I remember correctly, if you use this value, it doesn't work. So instead, I'm going to use 0.040 kilogram meters squared. Just because if you use the 0.40, you get negative. The speeds the question gives can't possibly work, so it has to be 0.040. Now at a certain initial position, the sphere's total kinetic energy is 20 joules. So Ke is 20 joules. And now our kinetic energy is going to be translational plus rotational. So our translational is just 1/2 mv squared, and our rotational is 1/2 I omega squared. We know that our omega is V over R. And we're given that our I, or maybe we're not given, but we can look up that our moment of inertia for a hollow sphere is 2/3 mr². So we can write this as 1/2 mv squared plus 1/2 2/3 mr squared times v over r squared. And I'm actually just going to rewrite this as Ke trans, just so that I can I can put this into some kind of fraction here. Okay, so then we can work this through here. So divide by that, 1/3 m. The r squared is going to cancel, so v squared. So we get 1/3 mv squared. And so then, how did I work this through here? So our rotational energy is 1/3 mv squared, which is equal to, it's equal to 2/3, sorry, nope. How did I do this here? Okay, I should have worked this through a better way here. Okay, what do I got here? So I'm just going to work it through this way. Oops. So my Ke total is Ke rotational. Yeah, okay. So this is 3/2. Okay, let's just multiply this by 3/2. Which will give us 1/2 mv squared. So that, which is equal to our Ke trans. So our translational kinetic energy is 3/2 of our rotational. There we go. So our Ke total is Ke rotational plus 3/2 Ke rotational. So we have this. If we multiply this by 3/2, then we get our 1/2 mv squared, which is our Ke trans. So that means our translational kinetic energy is 3/2 of our rotational. So if we put this into our total expression again, then we would get Ke total is 5/2 of rotational kinetic energy, which is 20 joules. So then our rotational kinetic energy is 8 joules. So that's how much of our initial energy is rotational. We want to know what the speed of the center of mass of the sphere is at this position. So if our rotational is 8 joules, then our translational must be 12 joules, as is what's left. So 1/2 mv squared is 12 joules. Or our V is the square root of 2 times 12 joules over our mass, which is given as, we're not given our mass, but we are given that 2/3 of mr squared is 0.040 kilogram meters squared. So then our mass is 2.67 kilograms. Meaning that our velocity is this over 2.67 kilograms, which comes out to be 2 times 12 divided by 2.67 square root. So our velocity is 2.998 meters per second. Okay. So that's our initial speed. And now when we've moved 1 meter up the incline, so now for C, we've moved 1 meter up the incline, and it's at a 30-degree angle. And so then our height here is just sine 30 times our 1 meter, or our height is 0.5 meters. And so then if we've moved 1 meter up the incline, we started with a potential energy of 0. Our kinetic energy was 20 joules. And now we've moved to a UF of mgh, which is equal to 2.67 kilograms times 9.8 meters per second squared times our 0.5 meters, which is equal to of course I didn't calculate it. Which is equal to 13.083 joules. So this is actually the point where if our moment of inertia was too large, then our potential energy there would be negative, which doesn't make any sense, as then the sphere wouldn't be able to roll up that far. And so then our kinetic energy initial has to equal our final potential plus our kinetic energy final. And so then our kinetic energy final must equal our 20 joules minus this value, which is equal to 6.93 joules. Okay. And then it wants to know the speed of its center of mass. Right, okay. I don't know why I did it that way, but whatever. Okay, so if it wants to know the speed of its center of mass, we can either use our relationship between our rotational or our or our linear energy. So our kinetic energy final is our 6.93 joules, which is equal to 5/4 of our I omega squared. And so we can solve for our omega as the square root of 4/5, 6.93 joules over 0.04 kilogram meters squared, which comes out to be 11.78 per seconds. And then we can get our velocity, our tangential velocity, which is also our center of mass velocity, as omega r, which is 11.78 per seconds times our radius, which is 1.766 meters per second. We also could have gotten the velocity directly from our kinetic energy final. Should be 3/4, 1/2 mv squared. 3/4 of mv squared. Right, I think. But, or from our original relation here, so that are as our translational energy is 3/2 of our rotational, or we could have used that our rotational kinetic energy was 1/3 of mv squared. But either way, there should be several ways to get at velocity from that. Okay, so we need all these pieces. So we can get the mass as 2.67. Like I said, we kind of need the moment of inertia to be the 0.04. So there's our mass. The initial kinetic energy that is rotational is 8 joules. So then our initial speed is this 3 meters per second. If we move up 1 meter, then we're going to be left with 6.93. And so our velocity again, we could arrive at it in several ways. So we could either use that our velocity is omega r to get 1.77 meters per second, or we could use the relationship between our total kinetic energy and our rotational, which is what they've done here, and you still get the same value. So that looks good. Okay, I'm going to stop this here and say that's all my questions for today. I hope you enjoyed this. If you did, please subscribe to the OneClass channel. If you want to leave questions, please follow the links below the video. This has been Jeff Krause for OneClass.